This was a really interesting project because all of our teammates bring in different skills and expertise to the table, and we wanted to combine mechanical, electrical, and computer science aspects and form one final product. So, how the idea came into being was that I was watching TV. I saw an ad for this wine glass that does not really tip over because it has increased stability, and they were targeting people with muscle and motor weaknesses. And getting inspired from that, I kind of realized that reaching for your nightstand is a hard task for people who have muscle and motor weaknesses. So our idea was to create this table on which there's an array of sensors, and when someone brings their hand near the edge of the table basically centralizes underneath the user's hand. The risk of getting injured in an attempt to reach to the table is greatly reduced, and thus it's really beneficial for people who have muscle and motor weaknesses. Here you can see the SolidWorks CAD design for our initial idea, and our goal was to create XY planar motion. So to achieve that, we have two separate mechanisms. If you see in the ground link, we have a slider that makes the links move left and right, achieving X motion, whereas for the Y motion, we have a pneumatic cylinder, which we later replaced with a linear actuator that goes in and out, helping us achieve the vertical or the Y motion. So you combine these two mechanisms with a stepper motor assembly and a linear actuator, and you can guarantee that this thing moves in all X and Y locations. Considering that we needed both horizontal and vertical motion in the XY plane, we achieve both of them in this mechanism where we have a 7-bar linkage. So the original requirements were to have a 5-bar linkage with a closed loop. The reason we didn't have a 5-bar is because when we had a ground link and we had the 4 bars up here, the extension in the y-axis was not enough. So we ended up using a 7-bar with a linear actuator that kind of extends it to the point where it looks and feels feasible. For the horizontal motion as well, we used a motor assembly, which we talk about later in the video, and combining both of them with an ultrasonic sensor, we have this XY plane motion. The creative aspect for this project comes in using the ultrasonic sensor and the automation, which actually can help people, as mentioned in the previous section. The first thing that you might notice here is the wall mounting setup. The idea was that this whole thing is portable enough that you can take the whole bracket and mount it wherever you want, and it should be functional immediately. So to kind of represent that idea, we made a makeshift wall, and we mounted the thing with these 3D printed mounts onto that wall. Now you might also notice that we use 80-20 aluminum bars that hold the entire mechanism and also allow for the timing belt to slide through. We have two spin motor assemblies which are powered through these Arduinos, and these Arduinos are then in turn powered through 9-volt batteries. Up here we have a 7-bar linkage as talked about previously, an ultrasonic sensor which is powered through an Arduino and a 9-volt battery down here, and we have a linear actuator at the bottom. To hold both of the linear actuator and the linkage system, we have a hub that was also 3D printed and a timing belt that goes through this. So for the wood part and the linkages themselves, we basically use Autodesk Fusion 360 to perform a stress analysis and figure out how much weight we can put at the edge. Then we took 3/4 inch wood and cut the wood pieces out. We even curved these parts out at the first ground link because they would basically collide with the hub, and we didn't want that to happen. So after cutting out the wood and having the links, having done a stress test, we knew how much weight we can support. Now you might be wondering how we figured what length of each link we need. We basically based our dimensions on the linear actuator itself. So it moves from here up to this point somewhere, and to maintain a uniform motion, we basically based our link lengths on the motion of the linear actuator itself. So the next thing is how we get the X and the Y motion. So for the X motion, we have a timing belt that's screwed into the hub, and we have two stepper motors that are just programmed to move in the same direction. We added extra shaft collars to give the timing belt additional support. So what really happens is when these motors move per se this direction, this entire belt moves this way and it pulls the hub with it towards this side and accordingly to the other side. So we get the X motion. For the Y motion, we have a linear actuator which when powered gives a 1,000 pound force, and it basically pulls the linkage system out and in depending on the polarity. Lastly, we have an ultrasonic sensor right here, and the idea behind that is if there's an object or per se a hand on top of that, it'll get the coordinates and it'll move towards the hand. So if I move my hand here, the sensor will try to follow it based on how it's coded.
Okay, so as soon as I put my hand on top right here, and I begin to move it towards me, the table follows me. And when I put my hand back and I push it towards the table, then it begins to move back towards the wall.
Y motion done, we use the stepper motor assembly for the X motion, which is left or right based on how the motors move. So in this setup, we coded both the motors to move clockwise, so this entire thing should move towards this side. However, what really happens when we power the motors on is something like this. So as you might notice, this thing didn't move at all, and the reason is the weight of this entire thing. To make it feasible for everyone and to make it lightweight and portable, we decided to use smaller NEMA 17 motors for this project, and we expected the timing belt to kind of roll over the thing, taking an inspiration from 3D printers. However, with the friction in the aluminum and then purely the weight of this entire thing makes it impossible for these motors to power this whole mechanism. However, to show you that this thing actually works and it's just not us blaming the motors, if I put my hand at the bottom to kind of give this entire thing a little bit of support, I can show you how this thing was really supposed to move. So I'll power these motors again and I'll give this thing the support, and hopefully it turns out how we expected it to turn out. Up close, we did put lubricant in here, and we did use specific NEMA 17 timing belt that aligns perfectly with the shaft holders. So to summarize, there's three main things that cause this issue. Number one, the motors are not providing enough torque for this entire mechanism to move. We're using 9-volt batteries here. And number three, basically why we're using 9-volt batteries is because during the design stage we were performing testing in the DFX lab where we had access to a variable DC power supply, and we were able to give this entire setup more than 9 volts, up to 12-15 volts, and this was able to move on its own, not as efficiently as we would want, but it was moving on its own. And considering that the DFX lab is closed till spring, we don't really have access to a power supply. And for those reasons, we were forced to use 9-volt batteries that kind of limit our motion. But in consideration of the few factors I just mentioned, initially this was a wooden tabletop that was going to be going on top of this linkage right here. But right now we have a makeshift cardboard top just so that we can hook our sensors up. And the reason we changed that is because, as I mentioned, this voltage and motor setup is not sufficient to hold the weight of the tabletop. To recap, our initial goal was to create a smart nightstand that helps people with muscle and motor weaknesses. Using stepper motors, a linear actuator, and an ultrasonic sensor, we managed to create a fully autonomous linkage. Throughout the course of the project, we did encounter a few problems, but we were able to overcome all of them, and the only visible issue we have right now is limited access to a power supply. And if per se the lab was not closed right now, we would have been able to demonstrate the full functionality of the system.